And welcome to the other half of the Chapter 6 review, where we're going to work a few selected problems together. So, starting with number 2, we have 4.59 grams of iron are burned and produce 6.562 grams of an iron oxide. Iron oxide means it contains iron and oxygen, and we would like to know the proper name. In other words, what is the charge of that iron? And in order to do that, we need its formula, right? So first, come up with formula, then we can come up with the name, which means we need to know the respective pieces, right? How much iron and how much oxygen. So if we take the mass of our iron oxide and subtract off the mass of the iron, we end up with the mass of, that's right, oxygen. Now, once we have the mass of the iron and the oxygen respectively, then solving the problem becomes just like every other empirical formula problem, where we start with our grams, and then we can convert to moles, and then from moles we reduce, and then after we reduce, we scale to a whole number as needed, right? And then once we have the formula, coming up with the name is just like we did in Chapter 5, where we work backwards and solve for the charge of the iron. All right, next problem. We have a problem that is a piece versus whole problem, right? We'd like to know the percent comp of each element in magnesium oxide, right? Where the piece is going to be magnesium and the whole will be magnesium oxide, right? Likewise, the piece will be oxygen versus magnesium oxide. So first we need a formula and we need its molar mass. So we will go and figure out the molar mass of magnesium oxide by adding magnesium plus oxygen, right? And that's the mass of the whole. Then we'll take each respective piece over it, right? There's 1 magnesium, so 1 times 24.31 over 40.31, and that's our piece versus our whole times 100. And we would repeat the same process for oxygen, where in this case it's 1 oxygen, so it'd be 16 grams of oxygen over 40.31 grams of magnesium oxide times 100, and that would give us our percent composition. Problem number 6, where we are given some percent compositions, and we are tasked with finding the molecular formula for sorbic acid, right? So what that means is we will start from our percents, right? Oh, well, actually what it means is step 1, solve for an empirical, right? Molecular always means find the empirical, and then we figure out what n is, right? That using the terminology from the book, what is the whole number multiple bigger? And then we can scale, right? So first, let's find that empirical. We're going to take each of our percents and we are going to assume them to be out of 100 grams so that each of those percents literally become grams of each individual element, right? And then we're going to take our molar mass and use that to convert the mass of each element into moles of each element. Then, once we have moles of each element, we will go ahead and do what? Right. Reduce, right? Always remember that we have to reduce. So we'll take those moles and we'll reduce them down. And then we will double check that our numbers are either whole numbers or within 300ths of a whole number such that we can round, right? And in this case, they do happen to be whole numbers. So we have our empirical formula. Then we have to calculate the molar mass of our empirical formula. And then we will take the molar mass of our molecule, divide it by the molar mass of our empirical, and that gives us our n, our multiplier. How many orders larger is the molecular formula versus the empirical formula? And then we multiply the whole formula by that number. And again, like we said in class, if this multiplier here, if this n is ever not a whole number, that's your big clue that you've done something wrong and you should go back and reconsider. All right. Problem. So number 7 is a word problem, right? Where it says isopropanol is composed of, has that chemical formula, and then acetone is the main component polish remover, and its formula is that. Clear liquids, strong odor, right? And we have something that is 62% carbon, and we would like to know which liquid is it, right? And that's a coded way of just saying which one is 62% carbon. In order to do that, you just need to do what? Right. Figure out the percent carbon of each formula, right? By taking the piece that is carbon over the mass of the whole, right? Molar mass of the whole. All right, next problem. Right. So if we read the next problem, we are tasked with finding the number of molecules in 15 grams of phosphorus hexafluoride, right? So molecules is our goal. Grams of phosphorus hexafluoride is our given. It's important to note that phosphorus hexafluoride is a molecular compound, which means that its particles are referred to as molecules, right? So I'm not trying to break phosphorus hexafluoride down, right? I'm just trying to figure out how many of them there are, right? So we're going from mass to molecules. So let's talk about how to do that. Back to our conversion map from the review that we talked about, right? We are given mass, right? So that's our starting point, right? And our goal is to get to particles, right? So we'll mark off mass. We're trying to go to particles. That means we'll use molar mass to get to moles, and then we'll use Avogadro's number to get to particles. So again, we will write down our given, which is our 15.00 grams of PF6, and then we will figure out the molar mass by adding all the components together. And then once we've done that, we will then use Avogadro's number, right, which again converts between particles and moles. And in this case, phosphorus hexafluoride is a molecule. So it means that's the number of molecules in 1 mole, right? And then we just solve and do the math correctly. Again, I cannot emphasize enough, right, that using that EE button on your calculator means you don't have to worry about your calculator breaking up your scientific notation. If you like the visual of typing in with the times 10 to the, please put them in parentheses. Like put your scientific notation phrases in parentheses. All right, now on to the next problem, which is similar but not the same. Phosphorus hexafluoride is a molecule, so if my question is asking for atoms of fluorine, that means I'm going to have to take my molecule and break it into its respective pieces. For the first round, I'm going to go ahead and take my 15 grams of PF6, and I'm going to use molar mass to convert to moles of PF6. Now, here I'm going to take my moles of PF6 and relate that to moles of fluorine in PF6, which would be 6, right? Now, this is what happens when you're not paying attention, right? I'd go from moles to grams of fluorine without thinking about it, and then I've got to turn my grams of fluorine back into moles of fluorine because that was ridiculous. And then now I can use Avogadro's number to get us to atoms of fluorine, right? Because fluorine is an element, elements are made of atoms, and that is the appropriate term, and we've done this correctly. Number 24, what mass of methane contains 35 grams of carbon, right? So 35 grams of carbon is my given. I would like to get to mass of methane. Carbon is part of methane. This is a piece versus whole problem. I'll take my 35 grams of methane or carbon, and then I'll write a mass relationship from carbon to methane, right? As in there are 12.01 grams of carbon in or equal to 16.05 grams of methane. And then we've solved our problem. Thank you for listening. Be good, practice, and I'll see you soon. All right, have a good day. Bye.